Alright, today we're solving Leetcode 416 called Partition equals subset sum. Right, so the problem statement says you're given a non-empty array of integers nums where nums of I is greater than 0, and what we have to do is we have to find out if the array can be partitioned into two subsets such that both subsets have equal sum. And we're given our constraints here, so the length of the array won't exceed 200, and it's always greater than 1. And like we said up here, nums of I is between 1 and 100. Now, we're going to be given an array. We'll call it nums. We'll say nums. So we're going to be given an array of numbers, and they're all going to be greater than 0. So say like 1, 5, 11, and 5. And we have to take values, we have to split this array up into two subsets such that both subsets, if you add them, all the numbers in the array, they have an equal sum, right? So what do we do to do that? Well, we know that if we're going to be dividing this into two different subsets, the subsets are going to have to be completely equal in terms of if we were to add the values of this subset or the entire array right here to get a total value. So the total would equal 22. If we were to divide this into two halves, each half would have to equal 11 in order for this to work, right? Because we're dividing this essentially in half such that, but the length can vary, meaning that we can have, like to solve this problem right here, the array would be 1, 5, 5. And then the other array, since we're splitting into two subsets, would be 11. Right, it's because 5 plus 5 plus 1 is 11, and then 11 equals 11. So that right here would be the answer to this problem, and if this was an input to our function, we would return a boolean of just true, meaning that it is possible to split this array up into two subsets such that they're both equal. Right, so what we're going to have to do to solve this problem is first we're going to have to calculate what is the actual sum we're going to have to calculate, and that is to get that we're going to have to add up all the numbers within the array and then divide it by 2 because we're only making two subsets from this array. Right, so the sum that we'll be trying to create is 11, and we're trying to see if we can create 11 twice in this array, essentially. And if we could do that while using up all the elements, we return true, else we return false. Right, so that's the problem. Hope that makes sense. If you can't tell, this is a DP problem. Hence the constraints being so low, meaning that solving this in linear time is, or at least polynomial time, is going to be difficult. But we'll see what we can do. Alright, I'm going to bring back the example I just said. We're going to have an integer array of nums. It's going to be 1, 5, 11, 5. We'll use the same example, right? And what we're going to have to be doing is we're going to solve this recursively, which means we're going to need a decision tree because we're either going to use the element or not when we're creating it, right? So after we calculate our sum, so our sum that we're trying to total to, remember, is 11 because we take the total and divide it by how many subsets we're creating. In this case, it's always going to be 2. So we'll take the sum which is equal to 11. And we can start our decision tree from here, right? We're going to be running a sort of backtracking function to solve this, a recursive backtracking function. And we're going to be making two decisions on each iteration of the array. We're either going to use the element, meaning that we're going to be subtracting 11 and 1, or we're not going to use it. And that's our decision, because we're trying to make a combination in which gets this 11 to 0, because that's the goal. It can't be less than 0, it can't be less than 0, and it has to be exactly 0 is what I'm saying. Right, so if we use, I'll make the left tree, we won't use it, and the right tree, we will use it. So in the right tree, I'll say 11 minus 1 is 10, and in this tree, we won't use it, which means we skip this index. We move right along. And then we look at the next index, right? And we have to make a decision based on this. So we have a decision again. Do we use this or do we not use this? If we don't use this, we're still at 11, and we're not using it. If we do use it, we do 11 minus 5, which is 6, okay? Now we're at 6 and 11. Well, technically, since we're running a depth first search function, hence the name depth first search, it's gonna run down the left side of the tree first if you make the recursive call of DFS without updating it. I'll get into the code later, but it'll run down farthest possible. It's not like a breadth first search where it just kind of spreads along a one-sided or at the same length, but anyway. All right, so here we are at 5. We just did that one, so we're moving on. 11. Do we use 11 or do we not use 11? Well, if we don't use 11, we're still 11. If we do use 11, we do 11 minus 11, which equals 0, which means we hit a base case, right? We hit 0, that's what we want. And since we hit 0, we can actually return out of this entire recursive function right off the bat, because we know it's possible. Because if I take 11 out of this array and subtract 11 from the total, that means if the total was 22 and we just took out a subset which was 11, then 11 has to be left, which means it is possible to create it. So we can actually return out of the function and don't have to compute all the other branches to save time complexity. So, but I'll finish the branch here so you understand what's happening. Anyway, so here we stop because we hit a base case, and on this side we're going to keep going and say, okay, we're at 5 again. Do we want to use this 5, yes or no? If we don't use it, we're right here. If we do use it, we're at 6. And since we're at the end of the array and we haven't hit 0 or a negative number, we return false because we can't go any further. Our array, we hit the last element within an array, there's no more numbers to calculate, which means the tree would end here, and then we backtrack our way back up here, and now we're at the 6. And at the 6, we have 2 different decisions. We just use the 5 so we can use the 11. So we do 6 minus 11, which would get us negative 5. Negative 5 is a negative number, therefore we would return false, meaning that is an invalid case. We cannot get negative numbers. It has to equal exactly 0 for this to work. Now, if we go down this branch where we don't use the 11, we still have options. We can either use the 5 or not use the 5. If we use the 5, and 6 minus 5 gives us the 1, and now we're at the end of the array, so we return false. If we don't use it, we're still at 6, and we're at the end of the array and haven't reached 0 yet, therefore we return false again. So from this left side of the branch, we've only seen 1 true, but of course that's all we need. But I'll explain the right branch as well. Right branch, we have 2 options. We just finished this 1 option, which means this 10 can go 10 minus 5, which will get us the 5, or we can keep the 10 if we don't want to use the 5. And then from here, we can go into the 11, right? So this would be 5 minus 11, which gives us the negative 6, which is a negative number, so we would return false. If we go here, where we keep the 5 the same, and then we don't use the 11, and then we go here, 2 more branches, we use the 5, don't use the 5. If we use the 5, we'll get to 0, which is another use case. And if you go back to the branch, if you backtrack your way up here, look at what we used, right? We used a 5, we used a 5 minus 5, so we used a 5. We used a 5 minus 5, another 5, and we used a 1. 5 plus 5 plus 1 equals 11, the sum, which is why we got 0. That's why we're getting 0 there, right? Which is one of the subsets in which is in our answer. And if you look at this one over here, we went down 11, 11, 11, didn't use any numbers until we got to this 11 right here and subtracted the 11, which got us this. Which is why 11 is in itself its own subset. So all we have to do is find 1 subset which equals 11, and then it works. Right, I could calculate this branch, but it won't lead to anywhere. Actually, it will lead to somewhere, probably just another 0, but you get the point, right? So we just finished using the 5, 10 minus 11 would be -1, then exit out, then 10, two options, 5 and a 5, so this would be 5 and this would be 10, and then we exit out, right? You get the point. So yeah, this is the decision tree we're going to make, and we're going to be writing a DFS function to do this. Now you got to take into account what is our base case as well, and also the time complexity. Now notice how there's 1, 2, 3, 4. The height of this tree is equal to 4. Now why is it equal to 4? Well, we have 4 elements. That's exactly why it's equal to 4. Our height of the tree will never exceed the size of the array. And that's very important to understand, because once you start talking time complexity, what is the time complexity? Well, you're making a decision which has 2 branches, a branch A and a branch B, which is 2, right? And then we have n nodes within our array. So our time complexity will be 2 to the nth power, which is an exponential time complexity, and something we're going to improve on, I promise. Now, this is an exponential function. This is not a good solution. This is brute force, which is bad, right? So how can we improve upon this? Well, we can use caching. Now we could use a map, which would map the instance in which we run into the same occurrences of the same problem. Now, the whole point of dynamic programming is that you don't compute the same steps over and over again, right? We haven't added dynamic programming yet to this solution. If we were to, what does that look like, right? So to cache this, we could use a map, but the problem with maps is that the lookup time, although on average case it's constant, that's only average is constant, but sometimes it's logarithmic, and we don't want to take the chance that sometimes if we want to look up something, we want it instantly in constant time. We don't want to have logarithmic time, because that just adds to the time complexity. That would be 2 to the n multiplied by the log of n, right? We don't want it more. If we don't have to do that, there's no point of doing that, right? So to counteract that and guarantee that we're going to use a constant value, what we can do is we can say, okay, well, we can declare a 2-dimensional vector of integers and the sum and index, because those are the 2 things that make up where we are in the tree. If we've already seen the current sum and the current index in our DP array, then we can return the value because we already computed it. So what does that look like? Wait, when we initialize it, we're going to have a vector of vectors of integers like that, and it's going to be DP, and the DP is going to be it's 2-dimensional, and it's going to be the sum. The size of it is going to be the sum plus 1 and the target. No, the size of the array plus 1. So nums dot size plus 1, right? And we're going to fill it up with -1 values just as a default to see. So if the array at the sum and the index does not equal -1, that means we've already seen it. And then we're going to turn that value right off the bat. So that will be one of our base cases. Also, if the value that we're looking at is negative, that is another base case. Or if it's 0, that's the only time we'll ever return true, if it's 0. And we only need to compute 1 0 to know that the function works, right? So by adding this, we will make this time complexity from exponential to polynomial, and it should be fast enough to work, at least against Leetcode's test cases. But yeah, all right. This is a 2-part video. One was the whiteboarding explanation, and the next one's going to be me coding it. And yeah, I'll skip that, I guess. Alright, before I get off, I just want to make one more point, what the returning is actually going to look like. So in this function, what we're going to do is we're going to be returning a boolean. So the boolean is going to look something like this, right? So we're going to return. We're going to return the DP of the sum, right, from our two-dimensional vector, sum by the index, which is going to be equal to the DFS function that we're going to write for the branches. But the first branch is using it, not using it. So in this branch, I'm not going to write all the nodes that go in here, but you get the point. This will be the not used branch, or the DFS of the used branch, right? And the only difference between these two branches is the actual subtracting the current sum by the current index. And that's the only two differences that is going to be between these two DFS functions. And we use this OR operator to return whatever one. If one's true, we'll return true. If it's they're both false, so we'll just return false. And we store that within our DP key, and we return it out of the function.